I want to talk today about serverless Rust. So I'm Stefan. For the folks who don't know me, I have the worst Twitter handle in the entire world, but I'm also one of the co-founders and co-organizers of Rust Linz. And over the last, let's say, 1.5 years, up to 2 years, I've done a lot about serverless. So serverless and serverless platforms and cloud providers who provide serverless offerings are what I do basically on a day-to-day basis. That's why I want to talk to you about serverless. I'm going to promise there will be some Rust, but there will also be a lot of cloud internals and things that you might don't know if you're using one of those serverless offerings. So who in here, who out here has not heard about serverless? You can raise your hand. Okay, so everybody heard about serverless. That's great. Usually so let's say serverless comes in a couple of different flavors, and this would be usually the point where I do this particular joke that, well, serverless is not actually serverless. There are still servers. You know, that's old. Everybody does that. The thing is, what I think nobody talks about is that there are multiple flavors of serverless, and depending on who you talk to, everybody understands something different. And one thing that serverless is the whole auto-scaling part. That's the infrastructure serverless, where you care about servers less, which means some cloud provider, whichever that is, make sure that all your infrastructure problems are handled. And usually, actually, this is one of the most important points. This comes with auto-scaling and consumption-based pricing. So this is, I guess, the most important distinction between all the other things. You just pay for what you're actually using, be that an entire server that is provisioned, or just, you know, a little bit of CPU, a little bit of memory, and there you go. The other part is more on the application developer side, and this is what is usually referred to as functions as a service. So instead of writing your entire server, HTTP server or whatnot, you don't write the entire server logic. You are just writing this little piece of logic that actually does something. How this is getting called, transferred, how the payloads are handled, how the responses are handled is not your part. You just focus on this little teeny tiny stuff that actually does something. And for some cloud platforms, this is actually often seen as some sort of glue code, especially if you think about AWS. AWS has 270 services or something around in the ballpark. You could basically run your entire application on AWS services. But you need a little bit of glue code to connect the bits and pieces and to make sure that all those services work together. And there are two, so for the auto-scaling stuff, there are lots of examples. One that came up recently is, or that I found out recently, is Google Cloud Run, which is really, that's my Docker file, do whatever you need to do with it, and AWS Fargate. And on the functions as a service side, so the two most well-known offerings are AWS Lambda and Azure Functions. And we are going to look at the internal of AWS Lambda and Azure Functions today. The thing is, consumption-based pricing and just writing business logic or just writing the functions, those two things can be seen totally separate, but usually they are working really well together. Azure Functions has offerings where you don't have serverless scaling, where you just say 100 servers please, and I write functions, but they are running all the time. They are all provisioned the entire time. This is possible. But usually you use them with consumption-based pricing, where I say, okay, I'm just going to pay for what I need, and AWS or Azure is making sure that we just need, that they just provision what I need. Which brings me to the billing if you use the two of them together. So usually most of the serverless providers say, we charge you for the time it takes to execute your stuff and the amount of memory that you need. That's very much simplified, but that's usually a way to calculate it. Calculation of serverless pricing is a hell. There are so many factors involved, and I'm going to get to that at the end of the presentation. there are companies specializing on calculating your stuff. So we are not going down that road. We are going down that road why we want to use Rust with serverless. And if you think about that, the entire pricing model of serverless is you pay for amount of time and for the RAM that you use. You have to say that Rust is really good at memory and speed. So you have really fast applications, and you know memory is everything that Rust is about. It's using just the right amount of memory, not having a garbage collector running, not over provisioning memory, just having what you actually use and what you actually need. And that's why I think Rust is a really good fit for serverless. Okay, let's look at two function as a service providers, two serverless providers. This one, what's that?
AWS Lambda.
Okay, for the folks in the stream, AWS Lambda. Well, no, it's the HalfLife logo, and not everyone is aware of that. So if you see any AWS Lambda blogs out there, they're usually using the HalfLife logo. Even AWS sometimes uses the HalfLife logo in their blog posts. This is the actual AWS Lambda logo, so get this in your brain. If you see that, that's AWS Lambda. The rest is HalfLife. And yeah, of course, we want to talk about AWS Lambda. And AWS Lambda, I couldn't say if it's the first one, but it's definitely a pioneer of functions as a service. So the poster child, one of the services that everybody has in their minds when talking about serverless. And I know it from making web APIs, and the more I spent with AWS Lambda, the more I found out that I guess web APIs is just a side effect. I guess this wasn't planned, that just works as well, because what it actually should be is just this little bit of glue code between AWS services. And that you have something like the API gateway that does HTTP requests or makes HTTP endpoints that you can call and make requests to. That you can attach a Lambda after that is actually, yeah, that just works. But I guess it's not the main use case, or Lambda was not designed exclusively for that. Lambda is very much unaware of triggers. It just takes an event that can be an HTTP trigger event, yeah. But what it does, it takes an event and it processes some workload and then it produces a result. It's like the classical function. You have some input, you have some output. In the best case, it's serverless. It's not stateless, which is not entirely true, but which is a mental model. And Lambda runs in very, very lightweight micro VMs, Firecracker micro virtual machines. And Firecracker is nice because it's written in Rust and it's a fantastic piece of technology. So if it's open source, you can check it out. There are some very clever things in there. And then you think about AWS Lambda, you shouldn't think about servers that are provisioned for you, where just write the glue code. They are actually workers. And this is a very important detail we are coming to in a minute. So if you're doing AWS Lambda, then I have to make my notes a little bit bigger so I can see what I've written there. Otherwise, it's becoming some sort of karaoke. Or look at that screen. So AWS Lambda, the execution lifecycle comes in a couple of steps, and what you see here in blue are all the bits and pieces that need to be run always, and all the pink parts are those pieces that we call cold start. So what happens when you call a Lambda, or when you start invoking a Lambda for the very first time? AWS does a couple of things. First, it checks if you're even allowed to do that. If you're allowed to do that, it checks if you are within the range of concurrent workers that Amazon can provide for you. And if that all is okay, AWS Lambda requests a worker. So you can think of a fleet of micro VMs, and you can request one of those workers to process your workload. If you get one of those workers, and if the worker is what we call cold, which means the worker doesn't know about what you want to process, the worker downloads some code, spins up or creates a sandbox, downloads the code, your stuff that you've written, and bootstraps your application. If you think about Node.js, this means that downloading your JavaScript files, downloading Node.js, downloading the Node modules, packing them in a folder, and then starting Node with the application and booting it up. And only then are your workloads processed. So this is the typical AWS Lambda execution lifecycle. A couple of the things need to be done always, but they are very fast, except those bits and pieces in the middle, the pink column. This can take some time, and this is the cold start time. If the payload is processed or the workload is processed, and you get another request, only the blue parts are running, which means AWS checks if you're allowed to do that, and if there's already a warm virtual machine, you are processing that code, or Lambda is processing the code. If you look at an invocation diagram, this is how the invocation could look like. You have a trigger, whatever the trigger is. Let's say it's an HTTP trigger. You're getting a yes.
How does after scripting work for this cold start? So you have this pipe VM, pipe tracker, where your workload is going, and you reached limit. So AWS needs to spawn or take a new worker. Will it be faster than initiating the first one? Or?
This is exactly what you're going to see here at the screen now. So, yeah.
Can you repeat the question?
Yeah, I'm going to repeat the question for the chat. How does cold starting micro VMs work if there are many processes running? Can I put it like that? Yeah, this is what we are going to see right now. So what is happening when one of those workers is provisioned? And what happens if you're already running a workload or processing a workload? What happens if another one is coming? So let's say you have a trigger. This can be an HTTP trigger, whatever, just a trigger. And this is the very first trigger that you have, like an HTTP request that you need to process something from a backend. AWS does its cold start thingy, which means requesting a worker, downloading an application, blah, 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 the entire thing. Once your runtime is bootstrapped, the runtime does an HTTP call to the AWS REST API. This is this /next that you can see here in the screen, which means it does a call to the REST API asking for the payload. So it asks, which event should I process? Can you give me all the information that I need to process my event? Once it has fetched this information, it processes it. This is the code that you are writing, whatever that is. This is the one thing that you are doing. Once the result is there, it does another HTTP request to the AWS REST API with a post message to response, giving the result. And during that time, this worker is exclusively working only on this particular workload, nothing else. Once the response has been sent, once the result is finished, the worker asks for another workload to process, for another payload from the trigger, for another event to process. If there's one, it grabs it from the queue, processes it, pushes the result back, and if there's none, it goes into hibernation, which means Firecracker is freeing up all the resources. So it stops, hit the pause button, resources are free, and another worker can get those resources. There's a certain hibernation period. If within a couple of minutes AWS is not open about the period, about the amount of time that needs to pass, but if this happens after the amount of period, the worker thaws again, so you freeze it, then it thaws again, which means it's not a cold start, it's still a warm container, but it gets all the resources back, it gets CPU back, it gets RAM back, and then can process another workload. Now what happens if you're processing a workload, but another request comes in? In this case, AWS Lambda spawns up a new micro VM. The entire thing doing a cold start, grabbing that payload from the queue, processing the workload, giving back the result, and then going into hibernation again. And this is actually the one big difference between AWS Lambda and all the other serverless offerings out there, which is that for every workload that you are processing, you have a dedicated worker doing that. No parallel processes within the worker or something. Not the thing that Node.js is really good at, which means doing I/O and being able to handle lots of requests because it doesn't actually do anything. It just has open I/O connections. Nope, you have a dedicated worker for just this particular process, and after that, it works on the next on the next process. Which also means if you get another worker spawned and this panics for whatever reason, which means, I don't know, Stack Overflow, heap overflow, anything, any panic that can happen, it just kills the particular worker or the particular runtime within the worker, and then it bootstraps this worker again, and then you can run the next payload. So this is how AWS Lambda scales out various workloads across its system. With the typical consumption plan, you get about 1,000 workers that you can use. If you need more, either call AWS or the events are queuing up, which means that you need to wait for them. Does this answer your questions? Cool, great. I already said that if those processes hibernate for a certain amount of time, they are getting disposed and resources get freed. So this is how AWS Lambda works. One thing or a couple of things that are good to know, which were kind of interesting to me the longer I worked with AWS Lambda, is that you are paying for RAM. So the amount of dollars that you are paying for scales within the amount of RAM that you use. So if you're using 128 megs of RAM, you have $0.000021 to pay. If you have twice as much RAM, you're going to pay twice as much dollars. But, and this is interesting, you're also getting twice as much CPU, which means that for most of the workloads that you're doing, it just costs the same. So if you don't have any workloads that need a particular amount of RAM that can work with a low amount of RAM, what happens is that if you get twice the amount of RAM, you get twice the amount of CPU, it costs twice as much, but it's also twice as fast, which means it levels again to the same amount. If speed is a problem with the application and not RAM, just go for the full gigabyte or for 10 gigabytes or whatever, it doesn't matter. It's the same amount of money that you're paying. Because if you have a smaller VM or smaller RAM, it just takes twice as long. And this is something that so I couldn't say that for any workload or for every workload that is happening, but that happens for a lot of programs that we have been running. So if RAM is not an issue, you can control the speed of the execution with that. All right, how are we going to write an AWS Lambda in Rust? Of course, we are bootstrapping the Firecracker VM, then we are running a node process because AWS Lambda is node everywhere, and node is going to load a WASM file, a Rust program that is compiled in WASM, so it loads the WASM file and starts the WASM virtual machine. And no, please don't do that. Please don't do that. That's way too many virtual machines. That's way too many turtles. That's sadly what you see in the blog posts on the internet. So if you type in using Rust with AWS Lambda, you're getting stuff like that. Not cool. There's a more concrete way to do that, which is, well, just compile a binary and let it run on AWS Lambda. So you don't need to have any other abstraction, and it's actually quite easy. So AWS provides a crate with a predefined AWS Lambda runtime, which does exactly that. It grabs something from the queue. Then you can write your handler function. You can see that here. And once you're done, you send a JSON result back to the AWS Lambda queue. Hi, drone. So this bootstrap part that you can see in this async main function, so it's async, which means you need an async runtime. Tokyo would be my go-to runtime for that, and this is also one that AWS recommends. But this bootstrap code here can be always the same. The handler function is the actual function that you are going to implement. So this is the actual logic, the actual code that you're running. Then you compile it to unknown Linux GNU. The documentation says that you need to compile it to Musel Linux. Doesn't matter, GNU works as well. It's just that with some glib versions you run into issues because the Amazon Linux version doesn't support a couple of symbols there. That's why they say in the documentation use Musel, because it's the least painful Linux target to compile to. It's also the slowest one. So go for this target that works. You might need to install a linker if you are on macOS or something, but usually that works. I have even some GitHub actions that compile that stuff for you. I'm going to show, to link to the repo where all that stuff is later on, so you can check it out. And name the binary bootstrap, that's the name. Put it in a zip file and upload it to AWS Lambda, and there you go. All right, let's look at some results. So, because Rust is really good at speed and memory. If I have a Lambda with 128 megabyte, and I run typical Hello World, which is just, okay, take the runtime from Lambda, the node runtime from Lambda, print out Hello World, and give the result back. A cold start takes about 200 milliseconds on a 128 megabyte Lambda VM. A rerun, so if the Lambda is hot, if the runtime is hot, takes about 2 milliseconds. In Rust, cold starts take less than 20 milliseconds. I couldn't tell if this is for the entire process that I have shown you, or just for the one particular piece that you have in control. Doesn't matter, this is what you're built for. So this is the number that counts. It's less than 20 milliseconds. So I had some cold starts in the ballpark of 60 milliseconds with the Hello World. That's great. And reruns usually are less than a millisecond, which is fun. So I had a couple of reruns where Lambda told me 0.5 milliseconds. Great. It also built me one millisecond because that's the smallest amount that Lambda can pay. All right. This is Hello World. This is not fun. This is not something that's in any way interesting. That's why I created a little benchmark program which is called Palindrome Products. What it does is that you take a range of numbers, let's say from 100 to 999. You create the combinations, like multiply 100 with 101, multiply 100 with 102, and do that with all possible combinations that they exist, and then see if the product is the same forwards and backwards. So 1001 would be a polynomial product because it reads the same from both sides. The nice thing about it is that this takes a lot of CPU if you're working with really big numbers, so you can benchmark really well how long this will take, because the bigger the range is, the more it takes. If I'm calculating polynomial products from 10 to 99, node takes for reruns, so I'm leaving out the whole cold starts because it's usually in the same ballpark as the Hello World. It's a very small program, so you don't have to do anything. Reruns are more interesting. And a rerun from 10 to 99 also takes 2 milliseconds. And of course in Rust, it takes less than 1 millisecond. Surprise, small numbers are fast, and surprise, Rust is fast. This is not something that you're interested in. What's more interesting is if you crank up the numbers, let's say from 100 to 999. 999 node takes about 500 milliseconds, and in Rust it just takes 45 milliseconds. So this is really, really fast. This is really, really nice. And if you're working with really big numbers, like calculated from 1000 to 9999, node takes about 70 seconds. And this is something where you hit a timeout very fast. You have to crank up those timeout numbers. Not so with Rust, because it takes about 8 seconds. So this is impressive. Of course, you can control it. Give it twice as much memory. CPU gets twice as much. Those times go down because it's twice as fast. But hey, same goes for the row down below. Same goes for Rust. But yeah, so those are the benefits of Rust in Lambda. First, one of the biggest benefits actually is that you have very, very small binaries instead of deploying the entirety of Node and your Node scripts and maybe a couple of Node modules or something. No, you don't have to deploy so much. You just have to run a 3 or 4 megabyte binary. You can unzip it fast. You don't have any overhead in bootstrapping it. This is actually the biggest benefits. This is how you get those nice cold starts, because you don't have any overhead from anything else. And it works great on low vCPU. So if for the 128 megabyte VM, you are getting provisioned something between a 12th or a 13th of a vCPU, which is not that much. And Rust, since it's natively compiled, works also really well with this kind of CPU units. We have low RAM usage, so what we see is that in Rust you are just allocating the RAM that you use. Great. In Node, it always tries to be ahead as much as you allocate. So which means that if I don't know, use 20 megs of RAM in Rust, Node allocates 40 megs of RAM. That's how the V8 works. But yeah. And also what I found out that you have less variation at execution. So if you're running benchmarks, which means I don't know, do 10,000 requests per second or something. See how Lambda behaves there. There are a couple of spikes where I don't know, you see that a VM is getting freed and or something queues or something like that, and then you can have spikes that even if your payload takes, I don't know, 45 milliseconds to run on Node, sometimes you have those 600 milliseconds or 1 second runs because Lambda can't handle it. If your execution times are very, very slow and very, very fast, Lambda is more able to handle that, so you have less variation in execution. And plus, it's super fun. So I love writing Rust, and writing serverless functions with Rust I love even more. Alrighty, cool. Let's go to the next provider, which is Azure Functions. And Azure Functions is very different in basically everything compared to AWS Lambda. So there are not that many overlaps, even if it looks like that. So when you're writing, I don't know, a Node application in AWS Lambda or Azure Functions, yeah, well, you're just writing this handler body and you're done with it. But there's so much nuance in basically everything that happens. So first of all, the triggers are part of the function definition. You define what your function needs to be triggered. You are defining the input and output binding. So you define the input, the trigger and the sink, like the target, while you're writing the function. In AWS Lambda, you're just providing the function, then you configure the inputs. This might be the same in the end, okay, of course, but it also means that you can use the same Lambda for various input sources and output sources, not so much for Azure Functions. You have to define the trigger with the function. You can have multiple output targets, yes, but they are very much tied to what your function looks like. It builds up on Azure Web Jobs. If you ever run across Azure Web Jobs and think, oh, that sounds fun, it sounds also like serverless, that's what runs there underneath. The most important difference, I think, is that the unit of deployment is not just a single function, but an entire function app. So you're rolling out the function app and you can put as many functions in there as you like. Let's say you put 10 functions in there. That's great. The function app gets deployed and scaled out together, which means if Azure Functions requests another server, there comes the server, not a worker, a server, it bootstraps the entire app, all the functions that you have in there. If there's 10 functions, all the 10 functions are bootstrapped. This is a big, big difference. This also results in big cold start times, but it also results in very low cold start times for I don't know, all the other functions in your app, because the entire app is booted up. Also, those are then servers, which means they can take more than just one request at a time. You don't have them exclusively. So it might be just like with any other server, with a node server or whatnot, that you need to process multiple requests in parallel. Alrighty, and it needs Azure Storage to store the function. So you can't deploy a function app without Azure Storage. Hidden costs. Just to say it. How does the Azure Function Execution lifecycle look like? So the scale controller checks if any events come in, and if those events come in and there's not a worker or a server already working on that, it allocates a new server. The server is unspecialized. So you can think of Azure having tons of Azure Function servers in their cloud, but they're all unspecialized, which means there runs the function host, but the function host doesn't know what to do. The function host doesn't know which functions to run. It just is a dedicated function server. Once it's getting specialized, the files are mounted to the server. Virtual file system, so the Azure storage stuff from your Azure storage is mounted into this particular server. The app settings are applied, which means, telling which version to use of Azure Functions, what the runtime is, blah, 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 all the kind of things. Then the function host, and I'm sorry, this is very small, the function host resets the function runtime, reads the function JSON. Function JSON defines the input and output bindings. We are going to see an example later on. Loads any extension if necessary. Then the function runtime and you're going to see that all in a second, loads the functions into memory, and then you execute the code. And you see there are lots of pink boxes, which means lots of stuff to do at cold start times. But you are also seeing that you have not so much to do when the container is already warm, when the server is already warm, because the scale controller says, is there an event, and the function server says, I'm going to execute it. So reruns are very, very fast. This is how an Azure Function Host works. So you get the trigger. The trigger is defined through the input binding. The Azure Function Host takes the input, and then it does either call an in-process task, which is written in C# or F#, because the Azure Function Host is written in C# on .NET. Also means that if you're writing functions in C# or F#, they're just getting linked together. I don't know if that's the correct word, because I haven't written any C# in over 15 years, but since it's the same technology, it just can run C# and F# stuff. If you're using something else that Azure provides for you, they have dedicated runtimes for that. You can see all those runtimes on GitHub. They are open source. And it calls this out-of-process runtime, which is either Node or Python or whatever, and it creates a gRPC connection with it. So it's sending events over gRPC to the function runtime. It processes those events in a gRPC-capable server and gives the results back. Third option, so those are not, they are not running in parallel, even though the image might suggest it. They're not running in parallel. It's an either-or. So you can either have in-process function apps or out-of-process function apps, or the third part, custom handler function apps, which means I give you an HTTP connection, do whatever you need to do. So this is where you can define whatever you like, be it a Deno process, like Deno is a Node.js similar language runtime for JavaScript, or Rust. So this is where we are going to implement our Rust Azure Function runtime. The results are going to be sent back to the function host, and it sends it to whatever output binding that you need. Stuff that's good to know, RAM scales to your needs. This is very important. So in AWS Lambda, you are going to pre-provision a certain amount of RAM that you are paying for. In Azure Function, it takes as much RAM as you need, not more, and you're paying for this amount of RAM that it takes. Also, the vCPU scales to your needs, up to one entire virtual CPU. Because Azure Function Hosts can do that. So it's not tied to the amount of RAM that you allocate or that you provision, just as much as you need. With the consumption-based plan, it scales up to one vCPU. If you have premium plans, you can have up to 4 or 5 or something. It's hidden in a number that's called Azure Computing Unit. And what I found out by Googling a lot is that 100 ACUs roughly are equivalent to one virtual CPU. Cold starts can be slow, but then again, since you have as much CPU as you need, those reruns can be very, very fast, and those initial runs can be very, very fast. And cold starts are for the entire function app. Alright, let's define the function host. So this is how it would look like if we are going to define a function host for a Rust application. There are two things that are important. So I'm not saying please do a Node.js application, please do a C# application, whatever. No, I'm saying I have a handler executable. So this is an actual executable like handler or handler.exe if you are on Windows, and enable forwarding HTTP requests, which means that I want to communicate via HTTP with my application. This is a function binding, where I say, okay, for the endpoint palindromes, I'm talking here now about HTTP endpoints because it's the easiest to do. Please create this binding where I accept get and post requests as input, and I want to see a result on the output over HTTP. So those are the two bindings that you can do there. This is actually something that I really, really like in Azure Functions, because you can, for example, write services that send an email but also give a response back to the user that calls it. So if you have, I don't know, send email with a body or whatever, you do an HTTP request, it processes your request, and then you send it to two different targets, like an HTTP out, so that the user in the browser knows what to do, but you're also sending it to SendGrid, sending emails. Alrighty, and now Rust again. Hey, we are at the Rust meetup. The nice thing is any server will do. So if you're using Rocket, if you're using what I have here, Warp or whatever, doesn't matter if you have a server that a server framework in Rust, or you're writing your own server altogether, it will do. That's perfect. Any server runs. Funny, it's called serverless, but you are going to write the server because, infrastructure serverless, not application serverless. Two things that are interesting. First of all, I need to have a path mapping that is equivalent to what Azure Function provides to me. So if I have, a palindromes.js in Node.js that is mounted at /API/palindromes, in Rust, I need to provide that name in my app. So it's just forwarding HTTP requests, it's forwarding paths. What comes in my server is that this is a call to /API/palindromes, and please process this event. So you have to take care of that mapping, which is a little bit of extra work because you have to create those folders with the function JSONs, but you also have to create the same mapping again. There's room for failures, for errors that you are going to have, I don't know, a typo somewhere because it's all strings, you all know that. The other part that's actually quite interesting is that you listen to a particular function custom handler port. This is a port that Azure Functions needs to spin up your server. This is an environment variable that gets forwarded to your application, and you listen to that port, which is also nice because if you want to try it out without Azure Functions, you just let it listen to any other port. So I have 3000 in this example. I can develop the server in its entirety on its own, and then, those 3 lines, perfect. It runs on serverless. It runs on Azure Functions. This is sweet, chef's kiss. This is wonderful. All right, a couple of results. Cold starts in Node, Hello World, Azure Functions, around 700 milliseconds, give or take. Can be 500 milliseconds, can be 1.5 seconds. Usually it's about 700 milliseconds. Reruns though, 1 millisecond, because then it's super, super fast. And this is now great. In Rust, those cold starts take less than 100 milliseconds. This is fantastic, because it's just so little to do for Azure Functions. I had cold starts in the ballpark between 30 milliseconds and 70 milliseconds, but 100 milliseconds is a good estimate, a good measure to say this is the cold start for my Rust application. Reruns less than 1 millisecond. Palindrome products, again for very small numbers, already great. Node takes about 9 milliseconds. Rust takes less than 5 milliseconds. The bigger the numbers get, I have about 80 milliseconds for Node. This was 500 milliseconds with the small AWS Lambda VM, and I have about 50 milliseconds in Rust. This was 45 milliseconds in AWS Lambda. The great thing is, if you have big numbers, it takes in Node about 10 seconds, and in Rust less than 1 second. So this is fantastic because CPU scales with it. But what you can see here, as well as with AWS Lambda, if you are doing stuff in Node or in Rust, factor of 10 is a good estimate. So 10x fast. What benefits do you have of Rust in Azure Functions? And we have a little lag here. All right. First of all, significantly lower cold starts. Cold starts was always a very big problem in Azure Functions, and they did a huge amount of effort to get that right. So I can remember presentations where I showed Azure Functions, and it took me 1 to 2 minutes to have a cold start of a Node.js application. Now with 700 milliseconds, it's really, really great, especially since reruns are so fast. But you can cut those cold starts down tremendously if you're doing Rust. What I found great, it's just a server. So any server will do. It doesn't matter which server that you use, even servers that you already have. They are immediately serverless, infrastructure serverless, because you just tell them this port, this path, and you are done. It's just configuration for you, and it runs in a serverless offering. You're just paying for what you need. That's great. Cold starts in Node.js or other runtime environments depend a lot on the amount of functions that you have, because all of them need to be compiled on cold start, not a problem with Rust. So this is also something to keep in mind. And again, it's a huge amount of fun. So I love writing Rust, and it's equally fun with Azure Functions. And this is actually my preferred way of doing servers right now. Just having Azure Functions scaling out my Rust servers, because hey, it just works. Alrighty, that's for the stats. That's for the milliseconds. That's for my tests. Summary. First of all, Rust should definitely be considered if you want to write serverless functions. It's a great tool if you like writing Rust. For some cases, you can benefit a lot, especially if you have processes that that maybe need to run in the background, that are CPU heavy, that really need to compute something, this might be your number one choice because it works great on low vCPU, it's fast, it needs just a little amount of memory. Rust in all cases can help significantly with cold start times. So if cold starts are your problem, Rust might be the choice for you. Execution times, I focused a lot on execution times. Keep in mind, we are not talking about hidden costs. We're not talking about Azure storage costs. We are not talking about AWS API gateway costs. Because this is, you get the HTTP bindings in AWS Lambda for free, big quotes. In Azure Functions for free. But in AWS Lambda, you have to activate the AWS API gateway, and there you're paying per traffic again. So it's calculating the entire thing is a nightmare. Seriously. I couldn't give you an estimate which one is cheaper. I honestly don't know. They're just too different, and I'm just running in free plans since the beginning, so I can't tell you which one is more expensive depending on the factor that you have. Doesn't matter, both get cheaper with Rust. So those are the benefits of Rust. If you want to read up on that, first of all, if you read up on Azure Functions, I can highly recommend the entirety of the Azure Functions documentation on what is that, docs.microsoft.com. They're excellently written. It's amazing how much information you get about everything in there. And if you don't find the information in the Azure Function docs, you find it on GitHub because most of the things are open source. So you can read up on the entire Azure Function host, how it works, on all the runtimes, how they work, and also lots of examples for other programming languages. So if Go is your thing, do it in Go. You have a tutorial for that. So this is great. One of my colleagues at Dynatrace has written a blog about what happens behind the scenes when AWS Lambda call starts. This is where I grabbed all the graphics from. It's a great read, check it out. And also check out the blog from AWS Lambda on the Rust runtime for AWS Lambda. This is where you're going to see a nice HalfLife logo, but also some great content for the AWS Lambda runtime. Last but not least, this GitHub link has all the examples from today, so you can check them out, like literally check them out, like Git check them out, and try them. And that's about it. Thank you very much for the